Hello, this is Ashit Mukunda. So today I'll be doing the video for homework 7. This assignment is all about high-level synthesis optimization. And then we have two parts for this assignment. So coming to the part 1. So part 1 was all about taking a C code implementation of a bubble sort, converted it to a BDL style that CWB, the cyber workbench, can synthesize and verify it. So I've done that, and then we proved our hardware worked by comparing its output to a golden software simulation. My final synthesized design had an area of 797 ALUTs and a latency of 16 cycles, which we can see here. So this was the code that I used for the BDL parsing or analyzing it, and then this was the report for the part 1b that I had to get it. So once I run it and then synthesize, I've got these data which says ALUT 797, registers being 92, DSP 0, block memory bytes or bits being 0, and latency index being 16, clock period 20 nanoseconds, which we have already set it in the project options, and then ports being 20, and then critical path delay being 21.7624 nanoseconds. So I've also attached a screenshot for these part. And then coming to part 1C, it was all about comparing the results between CWB and the quarters. So we did have few differences in the number of ALUTs and registers used on both the applications. And I've also attached the screenshot for both of these as stated in the question. And I've also written a small discussion about the differences. And then part 1D, which was about the bubblesort.c verification, where I had to do the simulation, both the simulations, one being software simulation and then one being RTL simulation. So with the software simulation, when I tried running it on the CWB console, so it did give me a small error or something like this. So I had to then use this command and run it on the Linux terminal so that I get the make file. Once I give the build, so I get the make file on the directory, and then I use that make file and then use the input data text and generate output data. That was successfully done, and these are the logs for that. And then RTL simulation again. This was the hardware simulation where once I did the software and then I had to verify with the golden output and get the data. So once I've done that, I've got the matches being 8 on 8, and then and this is the part where we'll perform a design space exploration. I will use HLS Pragmas, which are just special commands to force the synthesizer to build different types of hardware. Our goal is to see the trade-offs between area, the y-axis, or how much FPGAs we use for the design, and x-axis being latency, which is how many clock cycles it takes to run. So these are the three pragmas that were given to us. So beginning with design 1, design 2, and design 3. So I'll just show you my CWB. This is for the baseline where we just did the part 1. So I'm just gonna analyze this. So once I've analyzed that, it generates a light blue main folder under the bubble sort directory. So this I use to synthesize and generate. So you can look at the logs. So once this is open, we'll just close that because we're not going to look at that. And then you can see that this is the synthesis part is successful. And then I'll just open the synthesis results, synthesize window. So as you can see, so we have a small error, a small warning. That's fine. So if you just look at this, so we have in the graph 16 latency dots. This is for the baseline design. So if you just look at the QR report, you can see that it's the same thing that we got it in the part one. So this has not changed. So what we do is in the for the design one, we just delete this because we are just it's like cleaning the project. So I have I have the code ready for the different designs. So I'm going to use this code for the design one. So just copying and pasting it. So coming to design one, which is Pragmas array is equal to RAM, unroll times equal to all, and unroll times equal to all for the Pragma 3. So, and just for design one, the report asks us to use these conditions, unrolls for the both the loops. So I'm adding those Pragmas to my code. So you can see it's all being added in this code. So the array equal to RAM Pragma is the most important one here because it tells CWB not to use registers for the array, but to use FPGA's built-in block RAMs or the BRAMs, which are very efficient for storage and use fewer ALUTs as compared to the baseline design or the code. So obviously we expect the area to go down. So, but then again, however, BRAMs have a limited number of ports. They can only be read from once or twice per clock cycles. This creates a memory bottleneck. Even though we ask to unroll the loops, the hardware can't run in parallel because every calculation has to wait in line to access the RAM. So obviously we would expect the latency to go up, but not a lot, but yeah, it does go up a bit. And then I'll just analyze this again for design one. So let me just run the synthesis. You can see the progress over here, and we're just going to close this. So this is done. You just open the synthesize window. So let me just adjust to the readable window. So if you just see, look at this, the ALUTs, which is being the area, it has come down from 797 to 438. The RAMs have been utilized 64, the registers have come down, the latency index has increased, and then rest of the things just remain the same. So if you just look at this, we have a single dot at 56, which is for the design one. So just as we predicted, the area is much lower, down to 438 from 797, but the latency is much worse, jumping from 16 to 66. This confirms the RAM bottleneck. So this was part one or the design one. So we're just gonna remove this. So let me just quickly change the code to design two, which I've already saved it. So this is for the design two. I'm just gonna quickly analyze this, and then once it is done, I'll just quickly synthesize and generate the RTL. Synthesize window. So we're just not gonna look at the block number a bit. So I've just unchecked the option. So for the design two, the goal here was area equal to registers and then unroll equal to all on the outer loop and then unroll equal to 0 on the inner loop. So the unroll times equal to 0 on the inner loop is a key here because it is where all the comparisons and swaps happen in the code. By setting this to 0, we are forbidding the synthesizer from parallelizing this work. So it's forced to create a single simple serial circuit, probably just one comparator and one swapper, and then reuse that hardware over and over again. So we would expect this to be the smallest possible design, but also the slowest one because of these. And then, as we can see at the graph, there is we have a lowest area of at somewhere around 137 ALUTs, but it also has the highest latency, which is around 72, exactly 72. So this is our low area, low speed option. This was for the design two. If you just look at this, we have a single dot at 72 latency. So if you also look at the changes with the memory bytes, it's just not changed because it's still using the 64 one. So I'm gonna quickly do this analysis or clean this part and then again change the code to the design 3. So yeah, so let me just parse it quickly. So synthesizing and generating the RTL. So once this is done, look at the progress. So it's successfully generated. So let us just look at the synthesized window. So for design 3, the Pragmas was array equal to register unroll times on the outer loop was all, and then unroll times on the inner loop was all again. So just a small difference from the previous and this one design is that the inner loops was 0 for the design 2, and then for design 3 it is all. So so finally, for the design 3, we use array equal to red and unroll both loops. Yeah. So this is the full power version. We are explicitly telling CWB to use fast registers for storage and to build a massive parallel circuit for the sorting. And then, as we can see, the new dot for the design 3 has appeared. So if you just look at this, we have the same latency of 16, so it has just accumulated on this. So the exam again, all these dots have appeared in the exact same spot as our original baseline design that was without any of these Pragmas condition. So this is a great finding because it proves that CWB's default behavior was already to use registers and fully unroll the loops to get the fastest possible speed. Our baseline was already the design 3 version because again the reports everything says that it's still the same. So just to conclude, our design space exploration was a success because here the baseline code or the design 3 code, which is our fastest largest design at 16 latency and 797 ALUTs, and then our design 2, which is this, which used 66. So this is our smallest, sorry, the design 2, which used 72. So this was our smallest and slowest design at 72 cycles at 137 ALUTs, and then coming to design 1, which used 66 ALUTs and 66 latencies and 438 ALUTs. This is our ramp-based design, which balanced between area and latency. So This just shows how the HLS Pragmas gives us the power to explore these hardware trade-offs and choose the best design for our needs. Yeah, and then this basically concludes my demonstration for this part 2 of homework 7. And if you just want to look at this, so again there are like slight change differences between the memory block memory bits, and then coming to the reds, and then coming to ALUTs, and then there are a lot of other options that we can look at. So we also have delays at this point, and then this is the Word document or the report where I had to write in all of my results. So I've attached the same screenshots for the design, so including all the small description, and it also asked for other pragma suggestions. So just to find a middle ground between all of these conditions for the pragma that we use, we could partial unrolling is the best option because with cyber unroll times equal to 2 or somewhere around 4 on the inner loop, this would create a design that is faster than the fully serial design for the latency of 70 to 1, but uses again the less area that has fully unrolled baseline, which is 797. So yes, thank you, and this is the demonstration for part 2 of the homework 7. Thank you.